I'm assuming it's real hard. That looks too unstable. I can't be. You mean for our hemisphere? Yeah. Right.
All right, everybody. Thanks for coming this afternoon. I'm going to introduce Doreen. She is a third-year graduate student working on her PhD here. She's been working with me on at least what I think is a very interesting topic, where we're looking at making a climatology of rapid change events across Africa. So these are events that you could lead, like Flash Drought as an example, where you quickly descend into drought. But we have extended that to include 4 different types of rapid change events, and she's going to be talking about that today. She hails from Tanzania. She has 2 degrees. She has a bachelor's degree in meteorology, a master's degree in atmospheric and environmental sciences. Also has a background in broadcast meteorology, forecasting. So she has quite the range of expertise, and I am very hopeful that you will enjoy her presentation today. So, take it away.
Unmute.
Thank you very much,
Doreen,
Jason.
don't forget to unmute.
Sorry, I forgot to. Thank you very much, Jason, for introducing me. Good afternoon, all. Good afternoon, all. Today I'm going to talk about climatology of rapid change events and their fast flip, like the changing between wet state and dry state, and how they outpace, because this rapid change event, they outpace how we plan, how we adapt, also how we manage them throughout the season. And I'll look on how they link toward the sequence between the dry and wet states, looking at their rapid transition between 1 to 2, and then I'll link them to large-scale systems, specific for IOND and so, yeah. To start with, because many people that doesn't know me, then generally this is how my journey for the professional started. I started in Nairobi University. Actually, my mom, she's a meteorologist, and she's watching all the way from Tanzania now. They are alive, my parents, my siblings, everyone. So she has been my role model because she's a meteorologist. So I took my bachelor in meteorology in Nairobi University, then went to Hankook East in South Korea, taking my master's, and then now I'm in the West, taking my PhD. And since 2015, I've been working, doing a lot of things, among things, as Jason said, broadcast with a presentation, which are most of my things that are in YouTube, and then I've been also doing numerical as a prediction, dealing with WAF model, dealing with weather watch model and Cosmo model, and then I've been dealing with seasonal forecast and verification. To start with, I would love to acknowledge my acknowledgement for the God who helped me until today to be fine and to stand here and strengthen me. I would love to acknowledge my mentorship, like my advisors, professors, my committee member, Myra, and all professors who in one way or another, they empower me to be here until today. I would also love to acknowledge the people who fund my PhD until now, the donation from ESSC, George, actually, and Tanzania Meteorological Authority, where I work, where they gave me the permission to come here and pursue my PhD. I'd also love to acknowledge all supporting system in AOS. Chris, Dee was here, she retired. There was Stephen Ackerman, actually, he was the first person to talk to before I joined here, and various people. So from here in UW and others, they were from Indiana, where my husband is. I would like to acknowledge my families, the support from my husband, Paul, PhD in making in Indiana University, my parents, Pastor Mwara Shaw and Dr. Agnes Kijazi, my sibling, Engineer David Mwara, and my young sister, who is a doctor, and she has a happy birthday today. I wish you a happy birthday because she's watching all the way from Tanzania. Happy birthday to you, my sister-in-law, the wife of my young brother, and all my law is relative. I can mention all of them here, but I don't have time to do any of that. And I would like to acknowledge all the friends in the community. I know there are a lot of friends here from other departments. I've saw Ismail from Geography Department. I've saw Iran from the Political Science. All I acknowledge them, and all my fellow students, my love mate Shane and others who were here, they have already graduated. I thank them, and I sure acknowledge them for all their support until today. So let's start our talk today. Our talk of today will have like 5 things. I'll jump around from the introduction, and then I'll go until conclusion. Let's start with introduction. Why are we talking about rapid change event? We are talking about rapid change event because global the hydrological cycle is intensifying. A warmer atmosphere holds more moisture, storm can dump more water, and hot, dry spell pull moisture from soil and vegetation faster. At the same time, land use change such as urbanization, deforestation, and land degradation alter runoff, infiltration, and evapotranspiration. As a result, the greater variability in this hydrological cycle and hydroclimate, both in space and time. In some places, they see a lot of water. In other places, they see drier. They experience faster changes between the two. From the water balance lens, we are seeing more frequent shift between supply surplus, which is heavy precipitation and rapid runoff, and surplus deficit, which is excess demand, low precipitation, and high evaporative demand. This shift rearrange water availability and water demand for both natural systems like soil, vegetation, and rivers, and society systems like cities, farm, energy, and public health, from the global scale down to local catchment. As a result of this extreme event, due to hydroclimate events such as drought and flood, heat wave, are not statics. They are uniform with different places and states and regions. And they pose a challenge to human and natural system because this event, they are subscale seasonal, not like season-wise. How do we define rapid change event? We are defining the rapid change event as rapid development and rapid rate of intensification within short time, within weeks. And they differ with the conventional seasonal drought or like conventional season floods and all other hydrological. They differ because this one they take longer time, but this one they do short time. And as I've already explained in the first, like they pose a lot of challenge in forecasting, monitoring, and mitigation. Both our models and both our current system is like they cannot have this all transition captured very well. So today we are going to take on all specific 4 of them, the distance. I know there is maybe various of them, but today we are going to talk only about 4 of them. Flash drought, where is rapid transition extreme dry. It's like our threshold we use is 0.8. 0.8 is a standardized index. You can put any index. Most of the people, they use soil moisture, which is 20 percentile. So this is the same as saying like standardized ratio of, we'll see what we are using, of 0.8. And then there is a flash recovery, where it's a transition out of extreme drying, which is drought. And then there is transition to wet extreme, which is flash pluvial, and flash drying, where you are coming from the wet state toward the dry state. What are the causes of rapid change event occurrence? For the flash drought, they have been accompanied with high temperature, less precipitation, low humidity, high solar radiation result to increase of vapor diffusivity. While the counterpart of it, where we are getting out from the flash recovery, they are driven by heavy precipitation, rapid increase in soil moisture, decrease in atmospheric aridity, and as a result, there is a decrease of vapor diffusivity. When we go to the wet state, we have sudden intense rainfall, as well as increase of soil moisture, increase of atmospheric moisture contact and instability, rapid shift in soil moisture, abnormal warm condition after a period of high precipitation or high soil moisture. a lot of people, they have been laying on a flash drought and to detect that any other of these 4 rapid change events. And these are some of the detection method and indices have been used. Either they use soil moisture, where they check the drop between 40 percentile to 20 percentile. Either they use standardized moisture index, and goes further for high precipitation, for pluvial. Others, they have been linked it by pluvial flooding. Others, they say flash flooding, and so only, but they use precipitation. And other people, they have gone further to use the combined method instead of the single, like using only one variables. They combine precipitation with evapotranspiration, such as SPI, and then others like the ICPAC, they use combined drought indicator, which include a lot of things: precipitation, temperature, vegetation, and I can see also in USA, there is a drought monitoring, which is not a flash drought actually, but they use a lot of things, a lot of variables to detect them. What is the challenge in rapid change events? A lot of to start with, like rapid change event, flash drought. It has been talking since 2002. It was introduced, and then people like Newt in 2008, somebody started doing the ESI, but on 2013, Jason was the first one to start now saying flash drought, So he did the flash drought in 2013, and then they Newt in 2018. That's when this word becomes so popular around the globe. And most of the people, they have been saying that flash drought is contribute but around soil moisture depletion, and the decrease of ET ratio, evapotranspiration, actual evapotranspiration over potential evapotranspiration, or increase of evaporative demand. And others, they're just saying 1 to 2 things, like shift of the soil moisture, others precipitation, but not exactly people they have been talking about. 4 of them. It's like you'll find them saying just pluvials, which is hydrological, or saying just recovery, but it's not like, is this the rapid change or not? With this also, there is a lack of universal framework where you can define all 4 changes between wet and dry state. So therefore, this was like the motivation, we need to have something like that, not only flash drought. And most of the literature, they just bias on the flash drought. And why Africa specifically, not other place? Because most of the places in Africa, there is vulnerability to hydroclimatic activity. And most of the places, they rely on agriculture, and the adaptivity capacity is not well, and most of the rainfall over Africa varies across north to south of Africa. And climate models projection are showing that there is increase of warming, and it will shift the precipitation. As a result, it will create a lot of extreme events, or in one place, in another place maybe flood, another place drought. And there is few studies in Africa. As 2023, there was only 1 study of Africa, which just constitutes of South Africa. And then 2 studies about flash drought as well. They come up in 2024. So until now, I can say roughly there is only 5 studies in Africa, which are generally talking about the region of Africa. But other studies, in global, they just involve just some parts of Africa. Africa, its land cover, it's generally cover from high humidity, I can call the hyper humidity. Over this place is the Congo Basin. There is forest, high forest, as you know, the Amazon, where Ismail come from, Colombia there. Then there is Amazon. Then now I can say there is a Congo forest here. And then there is a dry Saharan region, like very, very dry region, the Sahara desert. And there is other semi-arid over the greater horn of Africa, and some kind of dry weather, dry desert as well as in Namibia, and other places it varies, but we are relying on the rain season most of the time. And when we can see the rain variability, there is a lot of variability on different places according to the land cover. But in annual wise, the precipitation ranges, it's moved. Like we can see when we start the year, the precipitation is over the south, and then it's moved over the middle of the year, March going toward to the south, and then comes back to south part. So there is all this activity which causes swimming of rain. So with hydrological variability, with all these changes and projection, a lot of things has happened back in Tanzania, where there is a lot of variability. And we can see, like here, I've just shown the example. The drought just happened in 2022, and people were not having water to drink. The livestock died and everything. And in Tanzania as well, just the other day, last year, people died, 155. So we really need this. We really need to know how to forecast this, how to predict this, how to monitor rapid change event to help with people, property, infrastructure, and economic. And limitation in Africa, we lack observation. Observation are few, and poor presentation in weather and model climates, both the regional models, the global model, and numerical as a prediction model. And the current monitoring system, like I talk about ICPAC, where they have the combined system, is working on agriculture drought. Therefore, there is satellite observation which help with this challenge. So with all this, we introduce the Hydroclimatic Rapid Change Assessment framework, which this framework, it's use the evapotranspiration data. ESR is the ET ratio between evapotranspiration, the actual evapotranspiration divided by potential evapotranspiration data. And then after that, we use different criteria to do this framework, like to check how does this varies according to our threshold, and then we can identify all the 4 types of rapid change events. With this framework, it will help to reduce the gap which is there, where there is no unified framework for predicting this or for identify these events. So it will help in reducing that gap, and as well the purpose to provide, analyze all these all the 4 rapid change events consistently. With all that, I'm starting my research question, where my first thing I'll say, what are the climatological patterns, like checking on the frequency, I call them counts, checking on severity, intensification rate of this rapid change event. And then I'll go to check on what are the dominant pathway. Is it from wet to dry, or dry to wet, or is it jumping from wet state to dry state? We will all see that. And then I'll connect them with large-scale drivers. Our data and methodology. I use GLEAM data, which is a global land evaporation Amsterdam model. It uses the satellite data, actually, and it uses one mathematics. It's called Payman equation to derive the potential evapotranspiration. And then I'll use Hadley's SST data for the large-scale drivers. And as we go further, I've divided my region into 7 regions. We did the K cluster, but it was not work well, so we just used our knowledge, just manual, to know where will we divide our regions. And then how it was rapid change event this detected. As I said, we started with ESR, ET ratio. They were daily data. And this daily data, they have a lot of variability. So we average them into pentad. And then after we average them into pentad, we went further and smoothed this data using smooth, like average mean, to get different composites of 3, 6, and 12 pentad. And after that, we did the ESI, which is called the standardized stress index, like evaporative stress index, which is a standardized one. We standardized what we had from our smooth composites. And then we went further and used difference method, where we difference all what we standardize with two change, like two pentad, to check all those abrupt change between the standardized ESI and ESI standardized change anomaly. And this method was introduced by Jason 2013. Yeah, he was introduced it, and people, they've never used it. And in his paper in 2018, he did something in soil moisture percentile, and then he just comments like, this methodology can be used even in standardized change anomalies. So when I came here, he just said, okay, let's do this other methodology. Okay, there are categories we use. The category we use, it was 0.8 threshold, like standardized 0.8, which is 20%. And we checked before this event to happen, what do we want something to be like? What do we want our ESI or our ESI standardized change anomaly to be? So we cannot say that we have a dry state when we have not come from anywhere. So before, our prior condition is like, for the dry state, we needed to know that it was above 0.8. And for the wet state, we need to know that in our prior condition, they were positive, like above 0.8, and so on. This is just example of one grid point, because we use at each grid point to do all these conditions. And what I can say, this where the first line, it shows that the offset, and depending on our scale, is like if our scale of ESI standardized change anomaly was 4 pentad below, then this our offset will be 4 pentad. If our scale was 2, then our time scale was 2, then it will be 2 pentad. If it was 8, then our time scale be prior to our onset of the event, it will be 8. And this line, it will show the onset, like the onset of our event. So this is for flash drought. Both of ESI, standardized change anomaly, and ESI, which it is state, the state line, all they're supposed to be below 0.8. And from this point of ESI is where we say this is our rate of intensification. What was the rate of intensification at the start of our event? So we use ESI, standardized change anomaly, to check the rate of each event at the start of the event. And then from the start toward the end, where ESI was getting out from this threshold, now we sum up all these ESI to get the total, and that we share is the severity. And the duration is from the start of the ESI to the end of ESI. The same thing happened, like for the Flash Pluvial, all the ESI, they need to be up. They need to be, ESI is needed to be in the greater than +8. And then we have the FR and FODR. Okay, the sequence event were obtained going forward and going downward, and we use short to long time scales. Going forward, just forward sequence, we are going from the dry condition to normal condition. The normal condition is like flash recovery and flash dry. And then going reverse is like we are jumping from the normal condition, and then we are jumping toward the wet event, or we are jumping toward the dry event. And then extreme sequence is like now we are coming from flash drought to flash pluvial, or flash pluvial to flash drought. And then we did like in each of the ordering, we make sure we count each block like sequence. How does this one event accompany to another one. And most of the time, at the end, we did something that's called coverage for risk maps, where we saw in each grid, it's like there is intersection where all the events they happen in that grid level, or there is a union as of which event happened. We'll see what's the difference between these coverage police. For large-scale drivers to show the relationship, we use correlation with different subregion, the 7 subregion level we use. Now I'm going to talk about the result. Let's start with the first question, where we want to see the climatology. Now this is the first results. I can say this is the frequency or the count. And the first row, it shows the time scale, which it was 3 pented composite with 2 change standardized change anomaly. And then the second one, it shows 6 pented with 4 change standardized anomaly, 12 pented with 8 change standardized anomaly. What we can see generally is like for the flash drought and flash recovery, most of the parts from the tropical region toward the southern of Africa has a lot of activity for flash recovery and the flash drought. And over the Saharan region, most of the flash drought there is no much of the drying which it can happen to cause that the normal situation in Sahara to be so much. However, we see for flash recovery, there is an introduction for this event that it shows how much there are some events which have happened, which were not a flash drought, but this area it was drying. Because it's not must that the flash recovery that we had a flash drought, but it's must that we had a drying prior. For Flash Pluvial, the same thing over the Congo Basin. There is no activity where you can see there is a lot of wet condition which it will cover more than what is happening in Congo Basin, like Congo Forest. However, over Sahara, actually, if rain there, automatically you have abnormality compared to what is there in dry. So there is a lot of activity over West Sahara, over this area is semi-arid in Somalia, going to Ethiopia, and then over the Kalahari Desert, also there is a lot of dryness. And then a lot of pluvials, yeah. And it's opposite when we are saying that flash dry, like we are coming from wet states. The same thing we see over Saharan region, west of Saharan region, over the greater horn of Africa, and then there is South region. As we go further, as we go to define our time scale, how do we see it? Like we have the same system, but they keep on reducing their intensity. Going to the next product, which it is duration. We know that it's like as we go further, this duration was almost in 10 pented, but as we go further, we see there is high intensity in the colors, which it shows that it increases, our duration are increasing. And the most of the duration of this event are showing in the flash drying, where there is a lot of this activity in Saharan region. Yeah. For severity and intensification, I just want to show 2 figures. This is just only for 3 pented. And then the upper one is intensification, rate of intensification, and the lower one is severity. So as we saw that in counting, that it was reducing as we move to higher time scale. What will happen for this one? When I want you to concentrate on this region, over the Congo Basin, and then over Saharan. The severity is less, but for intensification rates over this area, they are high. How about we go to the further end of introducing our rapid change event? This intensification, like the intensity of the color change, it shows that the severity, the intensification rate reduced. It's the same thing as we saw for drought, for flash For the county. For the county, we saw that as we move to the higher time scale, it decreased. So with intensification as well, it decreased. But for severity, it increased in intensity, as well as the what we saw in the duration. It increased from 20 percentile, from 20 pentad to 20, from 10 pentad to 20 pentad. Seasonally, there is the same trend as we increase our time scale, count, and intensification rates increase, but duration decrease, but duration and severity increase. However, now I want to show you how, as we remember for the annual cycle, where we have southern and then it goes to north and then going back to south, that's what you'll see now. Because from DJF, that is December, January, February, a lot of activity are in south part of Africa. But when you go for the MAM, the activity are like starting to transfer toward north part of Africa. When in JJA, the same activity of this county, they are transferred toward north. But when we are starting to go to the September, October, November, this activity are more in southern parts. But there is another activity here over the Mediterranean point. So the same trend, we see it in there as we go further to define our event. And this is intensification. It's the same thing for all of the season, but for Flash Pluvial, a lot of events are clustering in all east of south of Sahara region, south of Africa, and different area over the equatorial region. As we go further, this intensity of intensification rate, onset intensification rate decrease. Okay, now I want to wind up my first question to show that spatial pattern, most of the wet events are dominated in arid zone area, such as Saharan, while most of the dry events are dominated in humidity zone. And time sensitivity, like, okay, as we go longer time scale to define this event, frequency and onset intensification rates do decrease while the duration increase. And each event is independent because it's not that we want to see that there is a flash drought or anything else. And there is a seasonality where there is movement of this event, northward and southward. And MAM season, most of the time, is concentrated on the equatorial belt. Going to the second question, what are the dominant transition pathway and frequency of this sequence change of rapid change event? To start with our window, we select to use 1 month. We want to check this block of the sequence in 1 month, in 3 months, in 6 months, 1 year, annual, toward 3 years. And as I said previous was the forwarding. This is the forwarding, which now I'm calling physically consistent sequence, like we are coming from dry to recovering normal state, or we are coming from wet state, which is pluvial, flash pluvial, going to dry state. And then I'm calling it escalating transition. JSON, we call it whiplash event, where we say it's flash recovery and normal state, and we are jumping to wet state, or we are coming from the normal, like drier condition, going to drought state. And then there is extreme states where you are coming from flash drought to flash pluvial, or flash pluvial to flash drought. Starting with 1 month, here I'm just showing what's the difference between when we use union, like either one of the events to happen or not all events to happen. Looking at this place, the first one, the flash drought toward flash recovery, over Sahara region, we see that there is an event from 0 to 1. And then from the extreme part, where these events are not usual to happen because these are extreme events. We see all the African domain, like it covers all these events of 0 to 1. But when we go for the boss, where we really need one only, like in each single grid point, this event to happen, we see that even those events where happen only for one, they reduce. Even in this place also, we see the same thing, like other places, those events are gone. And now from onward, I'm going to use only the boss coverage states, what we are going to see here. So for 3 months, what I need you also to note is like our maximum number is 49, and those two numbers are 15. By checking from the left to right, this event tends to be more compared to the extreme event. That's one thing to note. And the second thing to note is the intensity, like the high amount of event over the west of Sahara region, over the north part of Greater Horn of Africa, like is Africa, and over the tip part of South Africa, especially for the wet states where we move from Flash Pluvial for Flash Drying. And the same thing is happening. Now we are moving from Flash Recovery, which it is the normal state, going to Flash Pluvial, and we can see the same thing where we happen to see here from the wet state transition is happening over this place, over the Greater Horn of Africa. And now it extends, like concentrate itself in Mediterranean areas. Over the dry state condition, there is changing over those areas, but it's not intense as we see as the wet state changes. It's the same thing, it's not showing so much, but we can see the extreme part. There is some kind of this event to happen here, and some here and over this place. When we go for 3 months, and we define with higher time scale, the same thing is happening over the Southern Africa, the north of Greater Horn of Africa, and west of Sahara region, Mediterranean. But those intensities tend to decrease in number compared to what we had with 3, because this one they are more, but this one now they reduce. However, for this place, they increase. As we add our time scale, this event tend to increase. The reverse events I call, or whiplash events, they are increased. Even this intensity here seems to have increasing. The same thing now, we are using 6 months. Now we are increasing our time window to check the block of this event. This event now tend to increase. The same thing is happening even for the whiplash event and extreme event. We can see now even over this area of our north part, there is an increase of those events. Going to 1 year. 1 year, there is lowest chance to see this event, but it's not that it's the lowest chance. Even if we see there is a few colors of green, they are kind of in 37 or 41. However, what we see between the whiplash event and the extreme event, there is now that chance. The chance is high. Likelihood is high for them to happen in all those hotspots. And now even there is introduction for this system over here. Most of the time is called intertropical convergence zone. And then 3 years, the same thing is happening over extreme event. So to wind up this question, I can say the dominant pathway in short time is flash drought toward flash recovery, or flash pluvial toward flash drying. As we move to higher state window, the wetter state is more dominant compared to drier state. And the hotspot areas, as we have seen, is the tip of South Africa, West Sahara and Mediterranean, some parts of Sahel, and north of the Horn of Africa. Sahara region had a pluvial and drying dominate compared to other transition, while as we move from time scale, from the low time scale to higher time scale, the spatial distribution do change and widen up. Now we are going for the third research question, like how does rapid change event connected to large scale drivers? Before I started doing anything like correlation or anything, I just explore and check which criteria shall I use, which threshold shall I use to define my, to define our analysis further. When I use 0.5 ENSO and IND, you can see there is a lot of this activity. This is ENSO for SON, like, because most of the research are saying ENSO and IND, they are strong starting from September going forward to December or January there. So as we go further, I started looking at SON, like September, October, November, until DJF, like the December, January, February, and checking what are these events happening and how many are they depend on the average of this season. When you check by 0.5, IND, there are so many compared to ENSO. When you go 1 threshold, they are so low. Therefore, I just say, okay, I'll use OND, the season of OND, October, November, December season, and I'll use ENSO as positive or negative 1, while for IND, I'll use 0.5 threshold. So this is the first result, which it shows how the correlation of different characteristics of this event, they correlate with different event. Looking at all these stripes, it shows the significance of correlation test of 0.05, less than p-value is 0.05. These boxes, I just wanted you to show you how this changes. These boxes over Horn of Africa, and so it's tended to act negative, like to have a correlation of negative toward negative part for flash drought. But for flash pluvial, the extreme part is positive, even for Mediterranean. While for Saharan and South Africa, it's kind of negative, it's kind of the opposite of what we had over Horn of Africa. When we go to Madagascar, it's coming back to how Horn Africa it is, and Madagascar is in south part of Africa, while Saharan is up. It is opposite of what we see in Horn of Africa. And over the flash pluvial, we have a lot of significance compared to other places. Another thing is like ENSO has a lot of areas over these characteristics where the significance of this event happened. And the significance, when we see the significance, is more than 0.3. Correlation of more than 0.3 until 0.52. There is another one where 0.6, but I'm not showing here. One thing also to note is like over Central Africa, there is no any significant over concern the ENSO. When we go for IND, those significant places, they tend to reduce in other sub-regions. But for Madagascar, we see only for the county, there is 2 areas for flash pluvial and flash drying. But the same thing happened over the Horn of Africa. IND, it tends to be significant correlated with IND compared to other places on every characteristics except for intensification. Mediterranean, few of them have happened. When we increase our time scale to define this event, the same thing is happening over Horn of Africa, but we see the places where, like for ENSO, the places where we had a lot of significance. If you recall that we had something here, but now we don't have like the significance, now it's not there. So as you change the time scale to define this event, other places they tend to be significant, to correlate well with this ENSO, but other places they tend to correlate different. When we do IND, the same thing is happening for for Greater Horn of Africa, but the values tend to slight decrease because it was 5.2 here, 0.52 here, it was 0.5, and now I can see 0.48. But the same, like, they have a significant. And over here, this region, there was not a lot of significance, but now we can see that there is a significant places over these things. So to conclude my research question, 3, large scale matters. I've not checked about MGO, but it is there, but I've checked only 2 of them, but they do matter. They do influence this rapid change characteristics in both positive and negative direction. ENSO and IOND over Central Africa did not show any correlation at all. And most of Horn of Africa, it had all the strongest like relationship of ENSO and IOND. Future work. My future work, like we want to check how does MGO phase change with this all rapid change event. The second is like we will investigate the spatial model to check how are the modalities, like how do these rapid change behave with like El Nino or La Nina, positive or negative IOND, and MGO because it's a large scale system, but it is only for a monthly wise, 30 to 60, 4 to 6 days. So it's nice to correlate it with all our sequence and our individual events to look on how it relates to MGO and other things. And then the fourth one, we will check on atmospheric system because as we saw this event have variability across all of Africa, the atmospheric system to check about the temperature, precipitation, vapor pressure deficit. We saw a lot of the what are the causes for this rapid change event. So we want to correlate them, or we want to see the composite and check how will this behave. And then lastly, we are planning like to do the statistical modeling and checking like, okay, which is it atmospheric, or is it large scale system, or is it land surface which are contributing to the happening of our rapid change event. Conclusion. I'll conclude that we did see the variability in rapid change event across all the parts of Africa. And then the sequence event also do varies regionals, they are not statistical. And do large scale events matter? Yes, they do matter. We have seen IOND and ENSO do matter. And therefore, with all this framework which we have introduced, it provides a foundation to define this rapid development and intensification of this rapid change event. And it will help to reduce the gap which is there in studies, like using the common unified framework for defining this event, and as well it will contribute in monitoring and early warning system. Asante sana, thank you very much, and I welcome any questions.
So thank you, Doreen, for excellent presentation. I guess we'll turn to the audience. Do any students have questions for Doreen?
Yeah, so thank you, Doreen. I was wondering, since you used ENSO as kind of like a large scale predictor, this is more of like a clarification question. Did you use like ENSO, like an ENSO different types of ENSO years, or did you use like ENSO as a threshold? Like when you use the 0.5 and like the 1, I think maybe I was just a little confused on that.
Oh, I did the average of season of OND, October, November, December for each year. And I took out like the, you call the mean?
Yeah.
Yeah, the mean of each to get like all the variability like of ENSO in each year and see which one was the strongest more than one threshold. Yeah.
Thank you.
Thank you. Welcome.
Thanks for an amazing Doreen, and sorry for a follow-up ENSO question, but I'm wondering, could it be possible that your OAD ENSO index has influence on some regions of Africa, but you are following GFM, and so you also have an impact on different regions of Africa, because there's a seasonality in interconnections as well. Could it be possible? Like, have you seen anything like that, or are you only look at OAD and not the winter like the GFM?
I didn't well understand your question, but I'll answer and then you'll let me know if I understand well. ENSO do influence a lot of parts in Africa, a lot of them compared to IOND, because IOND, it is like, I wanted to show a picture to help in a picture to explain this. Okay. Okay. IOND, because it's is an index where they use SST to minus west, minus east, while ENSO is over the Central Pacific Ocean. And IOND, most of the time, it influences some kind of these regions, most of the time, because we have also the monsoon wind, where they go to India, your place, Luria. And then ENSO is a large-scale system. It's connected with IOND, but it does, as we saw that a lot of variation, they happen from one end to another end. It does not vary so much. Yeah, it does not vary so much. But there is one system which is causing all this. It is the intertropical convergence zone, where the wind from the north and the south, they converge over the equatorial belt. And you talk about the atmospheric river the other day. So they connect with that because the ITCZ, intertropical convergence zone, it do move south and north, and it has arm of the north part. So it keep on moving this end and this end. And then over this area, there is a Siberian high pressure system. Over this area, there is Arabian pressure system. There is Santa Helena and there is Mascaline. When they intensify and they connected with ITCZ, they cause all these changes. But most of the time, because ENSO, it is started from September to December. That's why we see all this. But when you go for December toward February, it can shift all this activity toward north. We don't find a lot of activity here. I don't know if I answer your question correctly, but
Yeah, I was going for like the January to March.
yeah, because January to March, most of activity, they now started going upward, not in the equatorial region.
Okay.
Yes.
Thanks so much, Doreen.
Thank you.
So was your question actually about OND, October to December, versus like
January to March.
yeah,
So,
like your ENSO analysis was based on ENSO during those 3 months, and your question was what happened to the climatology and the relationships if you used the ENSO from a different 3-month period. That was your question, right?
GFM, because I don't study ENSO, but I've seen those teleconnection maps before.
Yeah.
And some regions did show that, like the southeastern African region would have a January to March teleconnection on OND. Would that affect
Yeah.
the formations
Oh,
or not?
okay. This one, it will go further with all the experience I have. Over the Greater Horn of Africa, because of the ITCZ movement, starting from November towards March, we always call that as a long season. Long rain season. November, December, January, February, March. Most of the events I'll talk with the experience of Tanzania. Most of the events, they cluster themselves in southern part. And also, over this area, it will create a lot of rainfall. While over this area and that time, over the southern part of Africa, it will be drying. La Nina is the one which is creating a lot of rainfall in South Africa. While over Tanzania, you will find out, and so as the El Nino, it's creating a lot of rainfall. So there's like different part over this one. But when you go for this area, like in Tanzania, for instance, in the north part, both October, November, December, and like the March, April, May, we do have all this season over this area. But when you go for JJA, over most of the part of the equatorial region is dry season, high wind. There is no rainfall. Because as we saw, like the ITC bed is already moving up. So when we use OND, we will not find any correlation over this area of Ethiopia going further to other area of central part. And there is I don't remember what the name of here. There is a wind which are coming from Atlantic. They collaborate with the Indian Ocean and causing the IT season to move over the east and west. So it depends on how you want to cluster your data, because if you are saying you are going to season, the season do change. Because like season in Tanzania, we have OND as our one of season, and then we have MAM. But over south of Tanzania, we have EJFM. While over people over Sudan and everything, what are the concern of them is JJA. Yeah.
Okay. Thanks so much again, Doreen.
Okay. Welcome.
This is a good talk. Within the span of your data set, has the land cover changed? And does that contribute to any trends in RCE, intensity, frequency, etc.?
Thank you. That's a good question. But I've not checked on land surface data. But automatically, if it is from 1980 to 2002, I'm having a picture where it shows Decado. It is not here, but it was here. It was here. We have removing it. But it shows all this variation of Decado. So automatically, if there is variation of Decado, automatically when the land change. Because of evapotranspiration, they each depend on land surface. Yeah, that is.
Any other questions? Okay, we'll go to Brad.
First of all, I learned an awful lot. It seemed counterintuitive that the Flash Pluvial would be over the Sierra and the Flash Droughts would be over the Congo, but that's because of kind of the baseline state, right?
Yes.
Okay. You talked a little bit in the end about the possibility of early warning. Seems like you're putting together a data set and the statistical analysis that would be ideally suited for some kind of a machine learning kind of application to do some early warning. Have you thought about that?
Yes, I've thought about that. That's why I have all these, the last statement.
Yeah. Yeah.
The last statement, like statistical modeling, employs statistical model like multiple linear regression to quantify relative contribution of atmospheric factor versus large-scale driver. This is like creating a machining model, including all these variables like for atmospheric and and the large-scale drivers and land surface like precipitation, evapotranspiration, and everything, and checking how does it contribute and how can they help to forecast our rapid change event.
Then a follow-up question. I didn't really understand why you went with the 3 different pentads. Could you elaborate a little? Like you're looking at 3 month, or you're looking at short-term, mid-term, or longer?
Yes. Yeah, because this event do tend to happen in sub-season timescales. So when I tend to do the 3 pentad, that's like 15 days. With 2 change is like 10 days. So it's like I wanted to check all these variabilities between short time toward long time of 2 months, like 12 pentad is those are 2 months. Because I'm looking at all these variabilities in sub-season time scales. Because most of the monitoring system, they are in the longer time scale, like 3 months for SA. And then others, they are like in 1 month. But they did not go below that. So I wanted to see the below that, like the shorter time scale toward the longer time scale. How will this rapid change behave? Yes.
Any other questions?
Forgive me if I missed this. So the definition of these rapid change events, are you using some sort of high pass filter to identify those, or is that just looking at just the change? You're not removing are you removing like a seasonal cycle?
Yes, I've removed all those. I've removed seasonal cycle. That's why I'm standardizing it.
Okay.
Yeah, I use the standardized data where I've already removed the individual pentad mean of all the time of my period, like from 1980 to 2022. So in each pentad, I've taken out the mean. Yeah, yes, yes.
Then just sort of a follow-up question on that. I know like in other areas, so in Indonesia, for example, where you also have a strong variation in Central Africa, the ITCZ, in Indonesia and Monsoon, that those rapid change events can show up as a delay in the onset. And the implications of that for farming is very different than just a change than just a standard rapid onset event, or a rapid change event. Because that delay is occurring, that delays the planting, or it delays the ability of maturation of seeds or something like that. Have you looked at the specific, like a synoptic analysis of like what does this rapid change look like in terms of like a few days before one and a few days afterwards? And
Oh.
what it actually, like, what are the systems that are there?
No, we have not looked at that, and that's something we are going to look at the next future work, like checking the atmospheric system and all these synoptic system. How do they influence the onset and cessation of this event?
Yeah.
Because as we saw that the rate of intensification, we define it as the time during this event that happened. How does this ESI standardized change anomaly happen when the onset, like the onset of this rapid change event? Therefore, it's like how, like you say, when we check back, we'll check how does this system influence our onset for our event. Yeah, so that's like a future work. Yeah,
Really nice. Thanks.
thank you.
We're still waiting for a question for John.
Dan pretty much asked my question. I'm really intrigued by what would be the actual events that drive, that instigate these changes, especially at the short time scale. And are the events themselves governed by something else? Well, that's kind of what Dan was asking, so I'm quite interested in that.
Okay. Next time. None. Thank you.
All right, so I see we're past 3:30. Any remaining questions? Otherwise, we'll give Doreen another round of applause.